In this video, we're going to introduce the Net Change Theorem. And the idea behind the Net Change Theorem is that there's a way to interpret integrals when we're talking about rates being given. And the main connection is the f, little f, is what we're given. If that's the rate of change, then if that's the rate of change of what we are ending up with in terms of values, our big F, then what we get is our integral equals f of b minus f of a in capital letters here. And this is the change, or the net change, in capital F over the interval a to b. In other words, just our end value minus our start value for this function. Where that gets more interesting is if we're talking about position, let's say x of b minus x of a, how can we determine the net change in position for a function or for an object? Well, what we have to do, or why we can tie that back to integrals, is if instead of putting a little f in here, we did this with x's here first, we would put the rate of change of what we're tracking, here's position. Well, what's the rate of change at position? It's velocity. And so if we want to find the net change in position, we can integrate the velocity over that same here time interval from a to b, and we'll get our end position minus our start position. Here's that same notation written out a little more explicitly. And here, just a conceptual difference in terms of which value we're thinking of versus the rate that we're tracking. The idea here is that the integral of a rate of change, so if we integrate velocity, we get the total change or the net change. That's what we get on the other side of our fundamental theorem of calculus. This can all seem pretty abstract, so let's take a look at some examples. So imagine we are given the velocity of a car, and it has a function here, and we also have a time interval from time 1 to time 5 in seconds. Then what does this quantity, the integral from 1 to 5 of v of t dt, represent? We'll ask you to pause the video and then check in after a moment. All right, if we take a look at the fundamental theorem of calculus and just use the recasting we just talked about, what we have here is our little f, which is big F prime, is our velocity. So make that more explicitly a capital F. There we go. And so when we integrate, we're going to get big F of t, but that is going to be our position. We'll call that x of t. So right away, from our earlier analysis, we know that when we integrate velocity, we're going to get positions. Specifically, if we're doing an integral from over a fixed time interval, though, we're going to get x of 5 minus x of 1. And that's going to be the net change in position of the car between t equals 1 and t equals 5. Notice it's not the position of the car, it's how far it has gone relative to where it started. And so that gives us some freedom. You can almost hear the plus c hiding in here somewhere. Depending on where we start, we're still going to travel the same distance with this kind of integral because all we know is the velocity, but we're going to get at least how far it traveled from where it started. Let's try another one just for practice. So here, h of t is the height of a child in centimeters. So this is going to be a more abstract velocity position thing. And we know that the child is 120 centimeters at age 10. Which of the following would represent the amount the child grew between t equals 10 and 18 years? So here we're going backwards. Take a moment to think about it, pause the video, and then we'll check in. All right, so if we're looking for the amount the child grew, that's the change in h, or we would call that the difference between h of 18 minus h of 10. And that is going to be equal to, working backwards, the integral of how quickly the child is growing between t equals 10 and t equals 18. So we're going to be looking just at this answer here. Now, there is an interesting answer down here in D. However, we just have to think about what the impact of that 120 is. So let's imagine a quick graph of the height against time. what we found out was that between year 10 and year 18, there was some growth, and we found that that growth, that net growth, was equal to the integral. So this change here, vertically, is the integral from 10 to 18 of how fast the child was growing over time. And the 120 would have been where we started at a height at time 10. And so this is our change in height, or our growth, plus the starting height. And so that together would give us something interesting, not the net change, but the child's final height at age 18. Because now we started at 120 centimeters, and this integral here represents how much we grew in the next 8 years after that, and so it gives us our final height at the end of the day. But the net change from the integral is simply the difference between whatever height we were at when we started and the height that we end at age 18. Let's look at one last example. Here we're going to work through some numbers though. We have water flowing into or out of a tank, so here we're going to allow ourselves both directions. And we're told that the rate of water flow is 200 minus 10t, and we can see the units here naturally fit into a rate, liters per minute. And we're given some information about the signs. Positive rates indicates flow in. All right, how much does the water level change in the tank during the first 45 minutes? Well, first off, we note that this is the rate of water change, water level change, or volume change. And so putting together our integrals, if we integrate r of t from 0 to 45, that is exactly the same thing as what we mean by the volume at time t. Oh wait, not the volume itself, but the derivative. So this r of t is exactly what we mean by the derivative of volume, or if you like, dv dt. Sometimes this can be helpful in terms of seeing the relationships. We can't cancel the dt's because we have a sum going on, some other stuff, but at least this reassures us that when we do this calculation, we are going to get volume information. And the fundamental theorem of calculus tells us that when we anti-differentiate our rate here, we're going to get our amounts, we're going to get volumes, and specifically the volume after 45 minutes minus the volume at time 0. So that's what we're going to get back, but we actually have enough information here to calculate that value. So 0 to 45, the formula is 200 minus 10t dt. The dt is important. And then we can do our antiderivative, 200t minus 10t squared over 2, add 1 to the power, divide by the new power. And we sub in our 45 and 0. And that'll give us 200 times 45 minus 10 times 45 all squared over 2. And then fortunately minus 0 minus 0 minus 0. That's nice and easy. So we grab our calculator and we end up with a value of negative 1,125. What are the units? Those are going to be liters. And that represents a net change in the volume. So this equals negative 1125 liters and implies a loss of 1,125 liters of volume, or liters of water. We know that this is a loss because positive rates, positive RTs or positive V primes represent flow ins. So if we get a negative value, that represents a net flow out. Now, of course, there's a little asterisk, of course, in this, which is we have to assume that V of 0 is larger than that 1125, i.e. that we started with enough water in the tank so that we could actually lose that much water without getting some weird time warp thing or having virtual water. More than 1125 liters. So, key concepts. When we're given this idea of a rate, the integral allows us to go back to not the actual amount, at least not directly to the actual amounts, but to the net change in those amounts. It's always a difference. End volume minus start volume. That's what we get out of these kinds of calculations. Same with the height. If we integrate how quickly something's changing, we get the change in height for this example here. And the example before, if we integrate velocity, the rate of position change, then we get the change in position or the net change in position through these kinds of calculations. And that is one of the major applications of integrals in engineering.